Thank you to Displate for supporting PBS. Antimatter drives sound like science fiction, but they may not be as far as you think. There's a version that could, just maybe, launch within your lifetime. Hey everyone, before we get started, 2 quick announcements. We wanted to let you know that your help with likes and commenting is working. Thanks to that, the algorithm is sharing current episodes with more of our community, so please keep it up. And if you haven't yet, subscribe and hit the bell so you don't miss new episodes. Next, if you believe in humanity's propensity for interstellar travel, we've got the perfect shirt for you. It fuses the Alcubierre warp drive with the X-Files I Want to Believe poster, and thanks to UV printing, it glows after sun exposure, even in the depths of space. There's 10% off for the first 48 hours, link in the description. Now, onto the episode. Warp speed, hyperdrive, jump drives, space folding, subspace wormholes, infinite improbability drives. We're pretty good at coming up with ways to travel faster than light, at least in fiction. Sadly, Einstein's relativity theory tells us that it's almost certainly impossible in reality, at least for macroscopic objects over meaningful distances. Probably our future exploration of the galaxy will have to take the slow road. That said, we can certainly do a lot better than the current generation of chemical rockets, which are still burning stuff for energy, you know, like a steam train. In terms of energy per kilogram, the antimatter drive is near as efficient as you can get, within the bounds of the laws of physics, if you care about those. As such, it's also a staple of science fiction, and as such, antimatter drives also feel as far off as the warp engine. But there have been a lot of advances in recent years that warrant this update on the timeline of antimatter-powered space travel. And there are early versions that you might even see launch. Let's start with the requisite antimatter review. We've talked about antimatter before, about how in 1928 Paul Dirac discovered it in his equations as he tried to bring quantum mechanics into agreement with special relativity, and found negative energy electrons. And how in 1932 it was discovered in reality when Carl Anderson noticed cosmic ray electrons curving the wrong way in a magnetic field. They proved to be Dirac's anti-electrons, positrons. So what is antimatter really? It's pretty fair to describe it as the mirror image of regular matter, and every particle of matter has an antimatter counterpart. It's the Bizarro to Superman, the Wario to Mario, the Dirac to Feynman, the same but oh so different. Antimatter is inevitable in a universe with the symmetries of ours. If we think of particles as swirls and vibrations in the quantum fields, well, those fields can swirl and vibrate backwards. The laws of physics are almost completely symmetric if we say flip all quantum charges to be their opposites, or reflect to the mirror image, or if we reverse the flow of time. Antimatter is the charge-flipped and parity-inverted version of matter, which can equivalently be thought of as time-reversed matter. The matter-antimatter symmetry means it's possible to produce particles of matter out of pure vacuum as long as you also produce the corresponding particles of antimatter to balance. And also as long as you have the energy to account for the new mass according to Einstein's equation, E equals mc squared. This process is called pair production. But if the laws of physics are symmetric in time, this process also works backwards. A matter-antimatter pair can also be uncreated, annihilated, to produce energy. And again, E equals mc squared, so take the mass, multiply it by the speed of light, which is a big number, then multiply it by the speed of light again, and you get a very, very big number. And that's why antimatter is the ultimate energy-dense spaceship fuel. For example, annihilate an espresso with an anti-espresso, and you get an explosion with the power of a modern H-bomb. There are, of course, complications to using antimatter, or we'd be flying around with it and blowing each other up with it already. It's very difficult to make the stuff in quantity, and even more difficult to store. And it's also complicated to harness it in rocket propulsion. But before we can talk about how we are solving those, we need to dispel a misconception. There's a commonly repeated statement that matter and antimatter annihilation releases pure energy. There's not really any such thing as pure energy. Energy is a property possessed by systems. It can take many forms: mass energy, kinetic, potential, etc. The most charitable interpretation of pure energy is energy that's easily accessible and usable. Mass energy is the least pure or free in that sense, and that's the price of it being the most compact form of energy. And that mass energy isn't necessarily all liberated in annihilation. That process will often produce other massive particles, so some energy remains locked away. The idea of this process of annihilation producing pure energy is probably from electron-positron annihilation. In that case, the ingoing particles have such low masses that the energy they produce typically isn't enough to produce other particles. Instead, they annihilate into photons and the rare neutrino. The entire energy content of those photons can be captured pretty efficiently. But to accelerate our spaceship, we really need momentum, not energy. Basically, we need to throw stuff out the back of the ship as fast as possible so that momentum conservation accelerates us forwards. Although our annihilation photons do have plenty of energy, they are massless and so carry relatively little momentum. Also, very high energy photons are hard to direct efficiently. Ideally, we want to harness whatever energy we produce to blast massive particles out behind us. It's certainly possible to do that with the energy of these electron-positron annihilation photons in an indirect manner, and I'll come back to those options. But there's another issue with this high efficiency type of annihilation, and it's to do with storage, which I'll also come back to. But all of this is nudging us towards using more massive versions of antimatter to power our spaceship. Massive antiparticles are much harder to create, but let's see where we're at with this. So, we had the positron in 1932, and the next anti-thing discovered was 2,000 times heavier, the antiproton in 1955, followed quickly by the antineutron, and then we started to produce antinuclei with antiprotons and antineutrons together, first antideuterium, then antitritium, then antihelium-4. More exotic antinuclei followed, with the current record being anti-hyperhydrium-4. All of these heavier particles are identified in the debris of high-energy particle collisions, which means they're both rare and difficult to capture. There are two steps to this. First, slow the particle down, then trap it. These collision products start out moving fast, often at a good fraction of the speed of light, and they're moving in random directions, so they need to be channeled and then slowed. The world leaders in this antimatter trapping are at CERN's antiproton decelerator. It's an anti-accelerator for capturing antiprotons. Once slowed, the antiparticles need to be trapped. This is arguably the harder part. If antimatter touches matter, it annihilates, which means there's no such thing as an antimatter-resistant material container that isn't itself made of antimatter. The solution is a non-material container, which means a force field, and the electromagnetic field offers good options for both charged and non-charged antimatter. The most famous container device for charged antimatter is the penning trap, in which electrodes at either end of the trap create an electric field that keeps charged particles in the middle along the axis, while a magnetic field along that axis prevents any of them from drifting away in the radial direction. This is the technology, for example, used by the BASE collaboration, who have managed to store 100 antiprotons for a full year in their larger penning trap. Electromagnetic containment like this relies on the antiparticle having a net charge, but that introduces a new problem. Like charges repel, and so a cloud of like charges ends up as a big diffuse cloud, which defeats the point of using antimatter as a compact, energy-dense fuel. Now, if you want to keep those particles close together, you can, but you need a colossal EM field with a similarly colossal antimatter containment device, again defeating the point. This is why we can't just use positrons or just antiprotons as fuel. Happily, there's a workaround. If you trap both positrons and antiprotons in, for example, the same penning trap, and then cool them, they'll combine into anti-hydrogen atoms. Of course, now you have the problem that the resulting anti-atom is electrically neutral and so immediately escapes the penning trap, which is presumably a bad thing. A more sophisticated trap is needed. The current trick is to use the fact that the anti-hydrogen atom has a magnetic moment like a little bar magnet. It'll try to align and move in the direction of a magnetic gradient. So, if you have a magnetic field with a minimum value in all three dimensions, any anti-hydrogen in that field will move towards the minimum and get stuck there. This is called a magnetic minimum trap. Because the new anti-hydrogen will immediately escape its penning trap, the magnetic minimum trap has to be superimposed directly over the penning trap. Now, the magnetic minimum trap is far weaker than the penning trap, and so anti-hydrogen needs to be really cold, colder than around 1 Kelvin to have a chance of remaining trapped. Various novel methods like laser cooling are used to further chill this anti-hydrogen. But despite best efforts, this whole process is still very inefficient, with only a tiny fraction of produced antiprotons and positrons being converted to captured anti-hydrogen. It's also difficult to keep much of the stuff trapped for long. The current record is by the Alpha collaboration. The team trapped 112 antiatoms for times ranging from 1/5 of a second to up to 1,000 seconds. Not exactly long enough for an interstellar journey, but now that we have actual anti-hydrogen, a new possibility opens up. Anti-hydrogen is expected to behave essentially identically to regular hydrogen, and that means if we have enough of it, it can undergo phase transitions into more useful forms. Hydrogen freezes at 14 Kelvin at atmospheric pressure, and so the hope is that enough anti-hydrogen would solidify at that point, and that's the dream actually, anti-hydrogen ice fuel pellets suspended in magnetic fields. Okay, so we have our antimatter fuel, let's look at how we can use it. Bring a hydrogen and anti-hydrogen together, and first the electron and positron annihilate, producing high-energy gamma rays. The following proton-antiproton annihilation is way more complicated. That's because we're really annihilating 3 quarks with 3 antiquarks, and they don't all annihilate. That only happens to the first quark and antiquark that make contact. They're likely to produce particles like a gluon or a W boson, which in turn create more quarks, fragmenting the 2 baryons into a shrapnel of particles like pions. Sure enough, this is exactly how antiprotons were discovered in collision experiments by Segre and Chamberlain in 1955. These pions give us another approach at antimatter propulsion. They can be used directly as our working mass, which means the stuff you throw out the back of your rocket for momentum exchange, for thrust. This design is called a pion rocket. It's possible because the charged pions can be channeled by a magnetic field. Unfortunately, the energy released in hydrogen-anti-hydrogen annihilation also ends up in neutral pions, gamma rays, and neutrinos that ignore our magnetic field. If we really don't want to waste the energy from these, there are other ways to capture it. One approach is to capture the photons and the kinetic energy of the particles to generate electricity. That electricity can be used to accelerate other particles to provide thrust, as in an ion drive, which we already employ for very steady if slow acceleration in spacecraft. And that can be done whether or not the annihilation products are also used for propulsion. And that makes it an option for electron-positron annihilation. Okay, so how long before we get our first antimatter craft? Well, quite a while for our first crewed interstellar craft, but maybe not so long for our first unmanned probe, especially for our own solar system. That might be possible if we use antimatter in a sort of hybrid mode with nuclear fission or fusion. Now, nuclear power is proposed in a couple of space travel scenarios. The more prosaic is a fission or fusion reactor generating electricity to power an ion drive. A more radical approach, but actually perfectly within our technological grasp, is nuclear pulse propulsion, like the Orion project. In these, a series of fission or fusion bombs are detonated behind the ship or behind a sail to propel it. Both direct nuclear reactor and nuclear pulse propulsion suffer from the same challenge, however. That is the size of the device needed. Fusion reactors need to be huge to sustain a reaction with net positive output. And this is why we don't yet have a commercial fusion reactor. Nukes need to be big in order to initiate their chain reaction. But if a small amount of antimatter can be employed to kick off the reaction, then these devices can be made much smaller. Let's take the H-bomb example. A key component of the hydrogen bomb is some sort of fission core, typically a ball of plutonium. This is surrounded by a layer of heavy hydrogen. The plutonium is detonated as a fission bomb, providing the heat and neutrons needed to ignite fusion in the hydrogen. Because of the need for a critical mass of plutonium, there's a minimum size for a hydrogen bomb, which means a minimum explosive output. That in turn means that any Orion-type spaceship needs to be pretty huge to capture and withstand that energy. But what if we replace some or all of the plutonium core with a tiny grain of antimatter? Then we can build a much smaller device of the same style, with the annihilation of the antimatter providing the energy and particle bombardment needed to ignite a smaller fission core or even to directly ignite fusion. Either way, this enables a much more manageable thermonuclear explosion, which would work on a smaller craft. This approach is called antimatter-catalyzed nuclear pulse propulsion, and more generally, antimatter-catalyzed fusion or fission may be useful in powering spacecraft in various ways. Really, the main advantage of doing this is that we need far less antimatter because most of the energy is from the classical nuclear fuel. The amount of antimatter needed is as low as micrograms by some estimates. It'll take us a few decades to produce even that much antimatter at current rates, but then we can build an antimatter-catalyzed fission craft that could reach the Oort cloud, further than anything we've ever sent out there, and that would be in a mere 10 years travel time. Or so at least one proposal has calculated. Other proposals for non-crewed craft are also within distant but not sci-fi future level reach. It's remotely possible that the first antimatter-enabled launch will be in our lifetimes, well, for some of us anyway. And not all of this is just theoretical. Early experiments have shown that antiprotons cause extreme amplification of fission in non-critical heavy metal samples. So we started out wanting a not too disappointing alternative to the impossible FTL drives. What's it really going to take to build a proper sci-fi antimatter drive? The main holdup is the rate at which we can produce and store antimatter. Once we can make enough to solidify, it gets a bit easier with the storage. At current rates, this is going to take centuries to millennia. So we can build more and bigger colliders that are devoted just to antimatter harvesting, but there's also the possibility of harvesting it in space. Space is full of radiation and high-energy cosmic rays, with high-energy collisions making antiprotons all the time. The Pamela satellite discovered that Earth's magnetic field confines antiprotons and positrons produced by those collisions. So maybe we can harvest this antimatter in the Van Allen belts to fuel up for an interstellar journey. A side advantage to harvesting in space is safety. I'm not sure that I would want to blast off from Earth's surface on top of a stash of delicately suspended antimatter. So that's where we stand with antimatter drives. They're not quite just around the corner, but there are also plausible paths to the first versions. And at least for those versions, the technical challenges seem pretty solvable. Our first crewed interstellar antimatter-powered spaceship is not in our lifetimes, but if we want it to happen, it will. One day we can cross the galaxy by annihilating the reflections in the quantum symmetries of spacetime. Thank you to Displate for supporting PBS. Displate posters are vibrant, high-resolution metal prints, including thousands of images from JWST and NASA. If you love engineering, Displate offers their blueprint collections, ranging from Saturn V rockets to imagined designs like Star Trek's Enterprise or Star Wars' Star Destroyer. Some feature Displate's Textra 3D posters with textured surfaces, contouring and selective gloss. They can be bought as collectibles to start a collection, or as gift ideas. Each one attaches with an included magnet kit, no drilling, no holes, which works for owners or renters. If you want to switch it up, the magnets work with any of Displate's 2 million plus artworks, and if you want a more personalised option, there's the new Custom Displates. With Custom Displate, you just upload a photo, artwork or graphic, get an instant preview, and you can turn any image into a high-resolution metal poster. Right now, by using the code Spacetime, you can get 33% off your order of 1 to 2 Textra Displates, or 38% off your order of 3 or more Textra Displates. There's details and a link in the description if you want to explore more.